Good afternoon. I am Nathan Weezy of Marquette University. This section we're going to talk about the Z-transform and converting stuff into the digital domain, a bunch of stuff dealing with digital filters. The first thing we're going to talk about is the Z-transform. Essentially what this does is this will convert a difference equation to the Z-transform, or to the Z-domain rather. And in the Z-domain we'll have a transfer function. Essentially a transfer function in the Z-domain is the same as a filter, is the same as a controller, which we'll see in a little bit. So let's do an example. So this is the definition for equation 1, how to convert a difference equation to Z-transform. Let's do an example. Let's assume that we have a difference equation. The y output at time n will equal, let's say that the input now and the previous input. So we're going to add those two together. And essentially what we're doing here to describe this in words is we're going to add the current input and the last input together, and that'll be the new output. And then we'll just do that forever. Okay, so how do we apply the Z-transform to that? Well, we just do this definition right here. It's an infinite sum for all the terms. So for instance, y of n will go to y of z times z to the 0 time. And that'll equal then x of z, again 0 z to the raised to the 0, and then plus x of z raised to the z minus 1. And that's z minus 1 is because this term's time delayed by 1. These other ones are the current delay. Now, we can solve this very easily doing some algebra for x of z to y of z and take a look at this. This will be our first Z-transform of the difference equation. What this will equal is 1 plus z minus 1. Okay, so that is now a digital filter actually, and this is the transfer function in the Z-domain for it. Okay, and one thing you can note is that this has just a 0 at minus 1, z equals minus 1. Okay, interesting. Now, you can have more complex filters, transfer functions in the Z-domain. For instance, we can arbitrarily describe any general transfer function in the Z-domain. H of z will be the transfer function, h of z. The a of z could be the input, and b of z could be the output. And then you can see that we have an infinite amount of terms, well, not an infinite amount of terms, capital N amount of terms for both the numerator and the denominator. Okay. In general, when we're dealing with controls and filters, this N order maybe only go up to like 2 or 3. Because you'll find out later as we go up above 2 for N, we're going to have some round off errors. So generally everything's constrained to an N equal to 2 or 3. All right, so let's consider this case up here. Again, you see this case here, 1 plus z minus 1. If we have a transfer function that looks like equation 3 here, well, guess what? This is the current, this is the time delayed by 1, time delayed by 2, time delayed by 3 for the input, and B0 through B3 are the coefficients in front of those. Now, what I've done down here is actually drawn equation 3 in a signal flow diagram. So for instance, the input will come in, we'll multiply by B0. The time delayed version of the input will be multiplied by B1. The time delayed version, the twice time delayed version of the input will be multiplied by B2. And the 3 times time delayed of the input will be multiplied by B3. And all those get added together to get Yn. So you can see that this signal flow diagram implements this transfer function here in 3. Okay, what's interesting about this is these are the type of filters called FIR, which stands for Finite Impulse Response Filter. These filters only depend on input. There is no feedback. We don't feedback the output ever in these. Now, there's some great things about FIR type filters. They have a linear phase and they're inherently stable. Okay, because there are no poles down here, there's nothing in the denominator, these are inherently stable, which is nice. Okay, so let's talk about a different filter. So that's essentially saying that all the A coefficients are 0, meaning there is no feedback. Now, let's go back to this case here. Let's say n is equal to 2, capital N. So we have 3 coefficients in the numerator, 3 coefficients in the denominator. And if we take a look at how this is formulated, what we have is this. So if you take x as z and multiply it over here to get your output, you'll see that we'll have x of n times b of 0 plus a time delayed version of x of n times B1, right? That would be this term. And then lastly for that, we're going to have a twice delayed xn times B2 added together. That would be this term. Now, that's part of the output, but the other part of the output is that we have a 1 times, so if you take y of z and multiply by over here, you have a1 times a time-delayed version of the output. So let's check this out. So here, I'll do this in a different color. Our output, which we're sending out time-delayed, times a1, this term here gets fed back into the output. And then this last term is a twice time delayed, that'd be this one. It's going through 2 delays times a2 back through to the input. So the output of this filter consists of both the input and time delayed versions of the input and the output and time delayed versions of the output. These are the respective gains, B0, B1, B2 for the inputs, and these are the respective gains for feeding back the output. Now, the interesting thing with this filter is when you're designing a controller or filter or whatever you're trying to do, this is the filter structure right here. All you're trying to solve for is B0, B1, B2, A1, and A2. What is the correct numbers to satisfy your goal, whether it's a control objective or it's a filtering objective or whatnot. Now, this type of structure where you're feeding back the output, this is commonly referred to as IIR filter, which stands for Infinite Impulse Response Filter. Now, these have also some pros compared to the FI filter. For instance, you need a lot less delays and memories in this type of filter to achieve the same type of objective that a FIR filter would need. Another thing too with the IIR is you can get really sharp roll-offs. For instance, if you want to specify just a really tight band on a frequency you'd like to pass and then reject everything else, this is the way you're going to want to go. It's going to be very hard, if not practically impossible, to pull it off an FIR filter due to the amount of memory that you would need to do. Okay, so those are kind of the 2 types of structures. Mainly what we'll deal with when we're doing controllers for now are IIR type of filters, okay? Now, I'm going to get some people asking probably about this filter structure. It's not the most ideal in terms of implementation, but the reason I drew it like this is just because it's very easy to visualize equation 4 with this type of signal flow diagram. There are other permutations of this that make use of less memory and are more efficient, but that's okay. That's really for a DSP type course. All right, so let's now consider, I'll start with an example of a simple difference equation. This is going to be very similar to the one that we dealt with at the beginning of this talk. So what we're going to do is we're going to say the output is going to depend on the current input plus the time delayed version of the input and divide by 2. If you think about this, what we're actually doing is we're taking 2 points. Let's say this was x of n minus 1. And we're taking this point, x of n, and what we're doing is adding them together and dividing by 2, we're going to get, guess what, this value. So this is actually a 2-point average. That's what this filter actually does. So if we take and go ahead and convert this to the z-domain transfer function, we get this. And of course, if we look at it, equation 6, we know that that is a FIR filter. There are no feedbacks to the output. All right, so what I'm going to do next is I'm going to put a step response into this filter. So equation 6 is our filter. It's a 2-point moving average. So here's this, to describe what a step input is, it'll look like this. So here's time 0, and it's going to be 0 for all time before time 0, and at 1 it's going to jump to 1. So this is 1. So these are discrete points. So this is a discrete step. All right, so what we're going to do is calculate what the output should be. All right, cool. So if we go ahead and step it, at time 0, we're going to add 1 and 0, right? And we're going to divide by 2. So your first output should look like this, 1/2. And then at time 1, we're going to add this one and this one. So we'll have 2 and we'll divide by 2, we'll have 1. So we'll have this. And then it'll go on forever because we have a step response. All right, so down here in the next page, what I've done is simulated this quickly in MATLAB. So you can see at time 0, this is the first term due to averaging 1 and 0 and divided by 2. You can see we have our 0 there. And then the rest of them are 1. So this difference equation, or this filter, is as simple as it gets. 2-point moving average. This will go on for all time. Okay, let's implement something else that we're familiar with in terms of control. So equation 7, this is another very common component that you're probably used to, but let's kind of describe what this actually is. So let's start right here, this part of equation 7. So we're going to take the current input and the time delayed version of the input, and we're going to add them together. Okay, let's look at what this looks like. So here we go. Here is x of n, and here is x of n minus 1. Fantastic. We're going to add them together, and then guess what we're going to do? We're going to divide by 2. Okay, so that's an average. So that'll look like that. Whoops. So we'll have some value like this, and guess what? We're going to times it by t. Well, guess what? The length of time between these two samples is t. So what do we actually just calculate? Right there, we have the area under the curve. Or in other words, this is commonly referred to as trapezoidal integration, right? So we have the area under that curve in the light line green. Okay, so we got that area, but guess what? What's the last part of this? The last part of this difference equation is we add the last input. Well, guess what? That's an integrator. We're holding the last input and we're adding a little bit of area for the next time step. And it goes on and on and on. So this difference equation is simply just trapezoidal integration, discrete trapezoidal integration. And it's not hard to understand this difference equation because they're just discrete points. Now, you can go ahead and apply the z transform, and equation 8 is what you'll get. This right here is what you'll look like in the z domain. Okay, perfect. Now, let's do a step input to this. Now think about it. This is again, a step input is going to look like this. It's going to step from 0 to 1 at time 0. So it's going to look like this. So we're stepping it, and it's an integrator. It's an integrator. Okay, let's see what happens. All right, so at time 0, we have this point here. Okay, what is that point? That point looks like a half. Okay, does that make sense? So we go up to here and look at our step input. We see that we're going to add 0, and we're going to add 1. We're going to divide by 2, so that'll give us a half, and then we're going to add the previous output. Well, the previous output was 0, so yeah, we should have a half. Okay, cool. So essentially what we just did was integrate this area right here. Next, we'll have another step at 1 like this. Time step is 1, so we'll add 1 to that. This right here is 1.5. And so on and so forth. 2.5, 3.5. And I simulated this in MATLAB, and you can see that. What do we have? We just have an integrator. We're integrating a step function. Okay, cool. So that looks good. We kind of understand a difference equation and what the transfer function looks like in the S domain. Or in the Z domain, rather. All right, so let's take a look at the pole zero map. So we can actually draw a pole zero map for these transfer functions. I'm first going to start with this one back here, which was just our 2-point moving average, equation 6. This does have a 0. It doesn't have a pole because there's nothing in the denominator, but it has a 0 at -1. All right, cool. So there's your 1, 0. You can see it there. There's nothing else here. Now, the interesting thing about the pole zero map in the Z domain is things kind of change a little bit. So you see this unit disk. As long as we are inside this unit disk, we are stable, which is different from the S domain. If we're inside this unit disk, we are stable. Okay, cool. So what happens is if you transform what happens in the S domain to this is how it maps. So the S domain, recall, if you're in the left-hand plane, you're stable. In the Z domain, if you're on the unit circle, you're stable in terms of poles. This doesn't have a pole, so remember how I said FIR filters are inherently stable? That's because they don't have any poles. So we don't have to worry about them being stable. All right, cool. Now, the next thing here, let's look at this. if you look at, so we have some lines on here, okay? So the biggest thing I'll point you to are these curved lines. And what these curved lines are again, damping ratios. So of course, if you look at this, where we'd like to operate in terms of a system to have a nice smooth response is somewhere close to a damping ratio of 1. And that is right along this line. And then here's 0.9, 0.8, and so forth. And then the natural frequencies, again, are these frequencies here. And they are in reference to your sampling frequencies. So that's why you see that capital T there. So they're in per unit of your sampling frequency. Okay. All right, so that's a pole zero map for the simple 2-point moving average. Let's look at the pole zero map of the trapezoidal integrator. And here we are. All right, so if we take a look at this, now you see, guess what? Hey, we have a pole over here at 1, okay? And we still have this 0 over at -1. But everything's constrained to the unit circle, so we are indeed stable. All right, great. So let's just take a look back at this equation here. You can see right here, this is where the pole is. And the pole, again, is at 1. And, of course, you can see our 0 again there. Cool. So that is for our integrator. All right, so there are different types of integration that you can do in the z-domain. It just depends on what you want to do. All right, so there is something called the forward Euler. There's backward Euler and there's trapezoidal. Okay, so what is forward Euler? Okay, so what is that? So what we're going to do is take the x value at the current time, and we're going to extend that forward to some value. Let's call this xn, call this x of n plus 1. And so this is called forward Euler, and what we'll do is we'll just integrate the area under this. And the length of this is t, of course, from here to here. So we take the current value times t, and we add it to our previous value. So this is a forward integration. It's not trapezoidal. It's not as good as trapezoidal in terms of approximating an integrator, but this is generally called forward Euler. And again, this difference equation is very simple to write down. So the next output will be the current output plus the current value times t. So this is our forward Euler. Now we can go ahead and z-transform this. It's not hard to do from here to here. If we z-transform this and solve it for x of z to y of z, or the transfer function, we end up with this. And take a look at equation 11 again. You can see here we have a 0 and we have a pole. Okay, the 0 is going to be at 0 and the pole looks like it's going to be at 1. Interesting. Now remember I said this was an integrator, right? It approximates in the Laplace domain 1 over s. So we can actually get a approximation between the frequency or Laplace domain and the z-domain by using forward Euler. So essentially what we're going to say is that s is approximating this right here. Okay, and it's 1 over s, so that's why we have flipped these. So what this is going to do is allow us to transfer a controller or filter or something we design in the continuous time to the discrete time by using this approximation here. For instance, let's consider this. We have a low-pass filter here in the frequency domain. Why don't we convert this to the z-domain by using the approximation in equation 12? Okay, that'll be interesting. Let's see what happens. So that's going to go into here and we'll be in the z-domain. So here's the transfer function now in the z-domain of this low-pass filter using a forward Euler approximation. Now, what comes out here? What I'm going to illustrate here is the step response of this low-pass filter to various levels or values of t, the sample time. So what I'm sweeping is this t here. And what you can see over here in the legend are the various t values I used. I swept from 0.1 to 2. Now the other thing I'll show you here is in gray I have the continuous time response, okay? All right, so first thing I did was 0.1 second sample rate. You can see that blue is pretty much lying right on top of the continuous time response. Then let's jump ahead to red and yellow. Red's a little bit above but converges back to it pretty quickly. Yellow jumps up here like this and then comes over. So yeah, you can see it's kind of diverging a little bit away from the anticipated response. Now let's look at 1.5 and 2. Well, here's 1.5 in purple. Look at this. Overshoot, undershoot, overshoot, and it resonates and comes back in, oscillating. And then look at the last one, this green. That's when it's 2. This goes up, down, up, and it looks like it's just going to keep oscillating. In fact, that is very close to being unstable. So that's an interesting thing to note here. In fact, if I go beyond 2, if I pick a value beyond 2, this will explode. It'll do something like this and just grow and grow and grow. That would be completely unstable, right? Well, let's look at the pole zero map and see what's going on. Here's our pole zero map for these various values of t, the sampling time. You can see we started originally over here at t equals 0.1 second with this blue guy. And as I kept increasing it, we moved to the red, then to the yellow, then to the purple. And look, the green is that one at 2 seconds. That essentially means I'm on the unit disk now. Now, if I go beyond 2, what you'll see is that I'll end up over here, et cetera, and this response will grow and grow and grow, be unstable, and that's because we're outside the unit circle. Now, you can also see that pretty easily from looking at the transfer function here. If t is greater than 2, you'll see that the pole here is some value outside of 1, meaning it is greater than 1 and we go into the unstable region. Okay, so that was our forward Euler. Let's check out backward Euler. Here's our difference equation for backward Euler. So we have essentially a value at time xn, and what we do is we take whatever that value is and equate that backwards, and we cover the area, we integrate the area. So it doesn't really matter what the previous input was, we just go straight back, times it by ts, so that's the xnt value there, and then we add it to the previous integrator output, and that becomes then our current integrator output. So this is called backwards Euler. Of course, we can transform equation 15, the difference, to the z-domain, which we result in equation 16. 16 you can just rearrange for algebra for 17. So this is the transfer function for a forward in the z-domain. Sorry, excuse me, backward Euler in that. Now, remember, that's 1 over s, so we can equate that to s, approximate it, and this is what we will get. So essentially what I'm saying is t over 1 minus z to the negative 1 is approximately an integrator. So if you rearrange that, you see you get this, okay? So that's an approximation called the backward Euler approximation. Now let's look at the types of responses and what we get if we use this approximation now. Here's the step response for those same various values I used in the previous example and the continuous times up there in gray. All right, so you can see again as I start in small sample time, they're pretty much sitting right on top of the continuous time response. But now as I go up, look what's happening. So consider 2, 3, and 5, which is this purple, this green, and this light blue. And you can see that this light blue here will jump straight up. That's the 5. Before, that one was way overshooting than undershooting. This green shoots up here and kind of converges. Here's purple. It doesn't matter. What the interesting thing here is that these all converge to the output of 1. Okay, so we don't have any explosion going on or any takeoff of values. So let's look at the poles and zeros and see what's going on with this one. Take a look at this. Here again is the pole for sampling time of 0.1, and as we increase the sampling time, we're going to 0.5, 1, 2, 3, and look at that, 5. That's as far as we get. That's interesting. The interesting thing that happens is if you let t go to really high, that x value will end up here. So no matter what you do when you use backward Euler, which is really nice, you always remain on the unit disk, which is a very important property of the backward Euler approximation from going from frequency domain to digital time domain. So that's great. We have a really good map here. Now let's do the last one, which is trapezoidal integration. Of course, we remember what this is. This looks like this. We have one sample here. We have the previous sample. And we essentially draw a line through it, integrate this area. This would be x of n. This would be x of n minus 1. We get that area, so x of n minus 1. The length of time here, of course, is t. That's our t by 2, so we divide by 2. And then we add it to the previous integrator output. So again, that's our trapezoidal integrator. That's equation 21. If we convert to, and we take the z transform, we get 22. If you rearrange and do the algebra, you end up at 24. So this right here is our trapezoidal integrator in this z domain, the transfer function for it. Now again, we're going to make this approximation. We're going to say, yeah, this is approximately equal to 1 over s, and solve for s. That just flips this. You end up with 26, this equation. So this is called the bilinear transform or the Tustin approximation. You'll see this a lot in DSP. What we're going to do now is take this again and insert it into our same low-pass filter example, and let's see what happens. If we do that, 27 turns into 28, and we get this equation for a low-pass filter using a Tustin approximation in the z-domain. Let's look at the step response. Oh, interesting. This looks interesting. So what's happening here? Okay, so again, the small samples times like 0.1, 0.5, they're pretty much sitting on the continuous time response. As we get up to, say, 2, 3, and 5, what you see here is here's purple, 2, that one converge after a step or 2. Here's green, overshoot a little bit, undershoot, and then converge. Here's blue, overshoot, undershoot. Okay, so what's happening here? It doesn't seem to be as drastic as the forward Euler, but it seems like this one potentially could go unstable. So let's look at the pole zero map for this one. All right, starting with the smallest sample time, 0.1, we're here again. And as we move up, you can see we're traversing again. Here's 0.5, here's 1. Ooh, look at 2. This is right on the damping line for 1. Now look what happens. See green, we're at 3 seconds. This damping line is no longer 1, it's actually 0.5. Then look at this one at 5. This one's approximately, we'll call it 0.35, 0.34, somewhere in there. That's the damping line. So essentially, we're traversing to our left on the pole zero map. We're getting more undamped as we cross 0. This whole line here represents 1, but once we get past that, we're essentially in 0, or we're decreasing in damping ratio rather. Okay, very interesting. The thing that we'll note is you can, as t goes towards infinity here, your poles keep moving like this, and they end right here, meaning they get on the unit disk, but they never pass it in the Tustin approximation. So you could still have a marginally unstable or marginally stable output. Essentially, it would ring back and forth. It wouldn't explode. So this is a good approximation to use. You don't have to worry about it going completely unstable, but you do want to check your poles, after you do the conversion to see where they land to make sure that you have a nice smooth transition, a nice, good, clean, damped response. Okay, thank you. That concludes this section.